Morning, everybody. We are into week 2 of the class. This week is going to be how the climate system works, which is a pretty important subject. So this is a good one. This is a good one to see because this is kind of the basis of all of climate science that most people don't understand. And if you can understand this, then you're in good shape for understanding climate change and climate science in general. So before we get started, I thought I should spend some time introducing myself. So I grew up in Davis, and then I got interested in science and math, so I figured astrophysics would be a good subject because space is cool. Who doesn't like learning about space, right? So I went to Berkeley, and I majored in astrophysics there. Got my degree in 2003, and then I went to UC Davis to get my master's degree in physics. Got that in 2005. And then I kind of changed gears. I got interested in the environment, and so I became an environmental scientist. And I got a job doing that in 2006. And coincidentally, that's the same year that Al Gore's film An Inconvenient Truth came out. And so at that time, I didn't really know anything about global warming. I just kind of had this vague idea in the back of my mind that global warming is a problem and we should probably be doing something about it. But I didn't really know anything about it. And so I remember I went to the Tower Theater with my wife, and we went and we saw An Inconvenient Truth. And I came out of the theater, and I remember thinking to myself, if the science in this film is accurate, how is it possible that we're not doing anything about climate change? And so one of the questions last week was actually somebody asked, was An Inconvenient Truth accurate and was it influential? And so for me it was influential because for me it got me interested in climate change. And I had that exact same question, is the science in this film accurate? And so then I spent the next several years just reading everything I could get my hands on, books, scientific papers, articles, anything, trying to learn about climate change. The short answer is that yes, the film that science in the film is accurate. There's a few little minor details that are not quite right, but the broad picture is correct. 95% of what's in the film is correct. And so that gets back to the question of why we're not doing anything about it, and we're going to address that as part of this class.
What's the name of the film?
An Inconvenient Truth is the name of the film.
Can you write it down? Because I can't quite make out what you said.
It's An Inconvenient Truth. Inconvenient Truth, yes. Al Gore's film. Right. So after spending several years kind of teaching myself about climate change, I joined this site called skepticalscience.com, which it's basically a myth debunking database. And so we're a bunch of international volunteers. Most of us have science backgrounds, and what we do is when we hear about a new climate change myth, we go to the peer-reviewed scientific literature and we read what the scientific literature says about it, and then we translate that into plain English and we put it into the Skeptical Science database to explain to lay people what the science says about the myth. And so at this point we've got over 200 climate myths in our database. And so pretty much if you've heard a climate myth, we've probably addressed it at Skeptical Science. And actually, in one of our upcoming weeks, we're going to do a whole lecture on climate myths, which is like my favorite subject. I love debunking myths, and so that's going to be a fun one. So try not to miss that one. So I started that in 2010, and then a few years later, the Guardian newspaper in the UK, they started an Environmental International Blogging Network, and so I applied to write for them, and they hired me on, along with my co-blogger, John Abraham, who's a climate scientist in Minnesota. And so that was in 2013, so I've been doing that for about 5 years now. In 2016, the National Center for Science Education gave me an award for that, so I'm like a friend of the Earth now, which is pretty cool. I've written some peer-reviewed climate science papers in my spare time. I'm also a member of this group, Citizens Climate Lobby, that we'll talk about when we talk about climate policy and solutions. And then a few years ago, I wrote this book. It's called Climatology versus Pseudoscience. It covers a lot of the stuff we're going to talk about in this class. Climate science history, myths, basic science. We got some like policy and economics in there, solutions. It's got all kinds of good stuff. When I published the book, I then found out that it's really hard to get people to buy your book. And so just be aware that you can buy my book on Amazon. It makes a great gift. It's great. It's great just if you want to learn more about climate change and policy and economics and all that kind of good stuff. This is my Guardian blog, which I write, I said, with John Abraham. He's the bald guy. I'm the good-looking guy. It's called Climate Consensus to 97% is the name of the blog. We're going to do a whole class on the climate consensus too. That's coming up in a few weeks, so that's another good one. That's one of my favorite topics, but we're going to hold off on that until then. But if you want to find the blog, you can just Google my name. You can go Google Guardian 97%. It'll probably come up, and so it's good to check out. I publish about once per week, usually on Monday, something related to preferably science, but lately it's been more about politics because our politics and climate politics has been kind of messed up lately. And so I've been writing a lot about that. But actually been writing a lot about California and what California is doing in terms of climate change. Next week I'll have something on Jerry Brown's, all the stuff that he's doing to address climate change for California. Okay, so let's get to the good stuff. How does the climate system, quick question?
Again, I just have a quick question.
Yeah.
What qualifications, what knowledge, what education does somebody need in order to be considered an expert in this area, expert enough to render a good opinion? I had a degree in chemistry. I'm not qualified to, I'm not an expert on climate change. So what are the...
Right, so the question is basically what background does somebody need to have to be considered a climate science expert?
Yes.
Generally, we say you're a climate science expert if you're actively studying and publishing scientific research related to some aspect of the Earth's climate. And there are a lot of different aspects of the Earth's climate, but there's sort of a general group that'll get lumped together as climate science. They can be studying the oceans, the atmosphere, all the different components. As long as they're studying something related to the Earth's climate and publishing scientific research about it, then we consider them a climate science expert. Okay, so the topic today is how the Earth's climate system works, which, as I mentioned, pretty important subject. If you want to understand anything about climate change, the science, or what we need to do about it, you need to understand how the climate system works. So we're going to start with a more complicated view of how it works, and then we're going to kind of boil it down and simplify it. So first, basically, you get incoming energy from the sun. That's kind of the on the left, that's the downcoming arrow. Energy comes from the sun, and then various stuff happens to it. Some of it bounces off of clouds and gets reflected back into space. Some of it bounces off of ice or other reflective surfaces, gets reflected back out into space. Some of it gets absorbed by the oceans or the surface, land. Dark surfaces absorb some of it, and then they send some of it back out into space as infrared radiation as heat. And then greenhouse gases absorb some of that, and they send it out into all different directions, downward, upward. So there's all these different components that kind of, basically they're taking the heat from the sun and they're moving it around the climate system. And we're going to talk about some of these individual components. We're going to spend some time on the greenhouse effect. But this is kind of the more detailed picture of how this all works. So let's just boil it down and simplify it. There's incoming energy and there's outgoing energy. That's pretty much the key concept related to climate change, climate science, and how the climate system works. It's the Earth's energy balance. So basically, when you have the same amount of energy coming in as going out, then the Earth is in balance. There's no heat buildup, then it's not cooling, it's not warming overall. There are still sort of natural cycles that cause internal variability and little changes in the temperature, but they're not. If you have this energy balance where the incoming energy is the same as the outgoing energy, then you're not going to have any long-term heat buildup. You're not going to have any long-term temperature change or wild big climate changes. The only time when you get big climate changes is when one of these arrows is much bigger than the other one. If you have more incoming energy, then heat's building up. If you have more outgoing energy, then the planet's cooling down. And so, for example, if you have a lot more outgoing energy than incoming energy, then you can start to go into an ice age. But this heat balance is really a key concept to understanding climate change. And so I kind of like this analogy where you think of the Earth as like either a water tank or a bathtub. And so you get water flowing in, which in our analogy is the heat. So your faucet's putting the water into the tub or the tank. And then there's outgoing energy, which is the outgoing heat, the air going upward. That's the amount of energy leaving the climate system. And so if in your tank you have the same amount of water going in as going out, the water level stays the same. It doesn't go up or down. If you have more water that starts to come in, then the water level goes up. If you have less water going out, if the drain gets plugged, then the water level in the tub goes up. So that's the water level in the tub going up is the equivalent of heat building up in the Earth's climate system. And if heat's building up, that's going to make the temperature change. It's going to make the oceans warm. It's going to make the atmosphere warm. And then you're going to get all kinds of climate changes resulting from that. So the key really is what factor is causing either the incoming energy to change or the outgoing energy to change. What's causing the faucet to put more water in the tub, or what's causing the drain to get blockage or allow more water to go out. So let's look at some of those individual components. And the sun is obviously a big one. It's responsible for almost all the heat on Earth. We get a little bit of heat from the Earth's core, but pretty much all of the heat on Earth comes from the sun. And so because of that, it's really natural for people to assume if there's a warming or a cooling on Earth, that it's probably due to the sun. So it's one of the most common myths is that global warming currently is just due to the sun. And this is just kind of this natural assumption. All the heat's coming from the sun. That's your one big incoming arrow into the climate system. And so if it's warming, well, it's probably due to the sun, right? And so this myth kind of, I think it frustrates climate scientists a little bit because they think, oh yeah, that big glowing ball in the sky, why didn't we think of that? Well, of course, we should have considered that for climate change. So of course, climate scientists have considered that the sun could possibly be causing climate change, and they have investigated that possibility. I kind of liken it to somebody who gets sick and then they go on to Google and they Google their symptoms and they go to the doctor and they say, Doc, I think I have scurvy. And then the doctor's like, yeah, let me figure out what you have. I'll figure it out. I'm the expert. So the good news for us on Earth is that solar activity is very stable over the long term. This is actually a nice chart of the amount of energy from the sun reaching the Earth since about 1600, so about past 400 years. So the past 40 years or so, we've had satellites in space that have measured the amount of energy, both incoming and outgoing, but they measure the amount of energy coming into the Earth system from the sun. And then before that, last week Tom talks about proxies, which are things that we measure that indirectly tell us how climate factors are changing. And so for the sun, one of them is just people observe how many sunspots are forming every year. And so for several hundred years, scientists have been watching the sun, looking at how many sunspots form. And generally speaking, the more sunspots there are in a given year, the higher solar activity is in that given year. And so there's these various different proxies that allow scientists to reconstruct how much energy has been coming from the sun to the Earth every year over the past 400 years and beyond, but this is the past 400 years. And so you can see there are periods where it's low, and then so in the 1600s, there was actually a period where it was particularly low. There was a very inactive period for the sun, and then it went up a little bit, and then it flattened out, and then around the 1960s, it went up a little bit, and then it flattened out. And so there's little wobbles and changes in the amount of energy coming from the sun reaching the Earth. But there is a key point to get from this, is that this entire increase from the lowest to the highest on this chart is a change in the amount of energy from the sun reaching Earth of 0.1%. So like I said, we're very lucky that the sun, its output doesn't change very much, because that means that the Earth's temperature doesn't change very much. That means the climate's pretty stable, and then it allows us to build, we can build farms and big farms in the same spot, and we can rely on the weather being pretty consistent from year to year, and we can grow the same crops in the same regions. And so it's just it's pretty much what's allowed human civilization to develop has been the fact that we can put these farms and cities in one place, and the climate stays pretty stable. And so we've been able to develop human civilization because of that. So coincidentally, that's one reason that climate scientists are particularly worried about climate change, because we've had this stable climate, and now all of a sudden we're destabilizing the climate. And so that's going to make, for example, agriculture is going to be much more difficult if suddenly the weather starts to become much more different than it's been historically in a given spot. And so we can kind of zoom in on that chart to the past 130 years and look at how temperatures and solar activity have changed. And so on this chart, the blue curve is measurements of solar activity, the amount of energy from the sun reaching the Earth since about 1880, and the red is the global surface temperature measurements, which we started in we have pretty good records since about 1880. That's when they're most accurate. And so you can see in the early 1900s, they both went up a little bit, and then in the mid 1900s, they both flattened out a little bit, and then since 1960, global temperature has really started to go up really fast. And since 1960, the amount of energy from the sun has been pretty flat. It's actually gone down a little bit, especially over the past decade or so. We're in a really low activity phase of the solar cycle. And so over the past decade, we've actually had some of the hottest temperatures ever recorded in human history. And at the same time, solar activity is going down. So basically what that tells us, the amount of incoming energy from the sun is not going up in recent years. In the past 40 or 50 years, it's actually going down a little bit, while the heat in the Earth's climate system has been going up. And so basically, if we go back to our bathtub analogy, the water level is going up, but the amount of water coming in from the faucet is actually going down a little bit. So that tells us that something else is causing the water level to go up. Probably there's a blockage in the drain, and then you have to figure out what's causing the drain to be blocked. So then we can look at some other components. Volcanoes are a pretty cool component of the climate system. And so when you have a big volcanic eruption, it puts a lot of stuff into the atmosphere. It puts soot, it puts sulfur dioxide into the atmosphere. And these things block sunlight. And so when you have a period of particularly high volcanic activity, it's putting a lot of junk into the atmosphere, and that's blocking sunlight. So less sunlight is reaching the Earth, reaching the surface of the Earth, and so that's causing the temperature at the Earth's surface to cool, just because there's less incoming energy, not because of the sun, but because stuff in the atmosphere is blocking the sunlight from reaching the surface. So then conversely, if you go from a period of high volcanic activity where there's stuff in the atmosphere, and suddenly there's a period of low volcanic activity, so the atmosphere kind of cleans up, and then so more sunlight starts to reach the Earth's surface, and then so in these periods of low volcanic activity, temperatures go back up, just because there's more of that sunlight reaching the Earth's surface. And so actually, for a long time, climate scientists thought that solar activity was a really big driver of temperatures on at Earth's surface, but in recent years, they've kind of started to shift and to think volcanoes and volcanic activity over the short term has a bigger influence on Earth's temperature than changes in solar activity, just because the changes in solar activity are so small, as we saw on that last slide. And so over the long term, that's different, but at least over the short term, in terms of decades and centuries, volcanoes in the short term have a pretty big influence on short-term temperature changes. Over the past century, we haven't had any particularly low or high periods of volcanic activity. It's just been kind of average. And so over the past century, volcanoes haven't had a particularly big influence on the Earth's temperatures. Over the short term, we've had a few large volcanic eruptions so if there's a given year where we have a big volcanic eruption, there's been maybe half a dozen of these over the past century. Then over the following year or two, there's enough stuff in the atmosphere that does cause a temperature, 1 or 2 year temperature drop at the Earth's surface. But that stuff that gets shot into the atmosphere from the volcano, it washes out of the atmosphere pretty quickly, and so it only has an influence for about a year or two, and then after that, temperatures kind of go back to normal pretty quickly. So then we have human pollution. When we burn fossil fuels, we also put a lot of sulfur and junk into the atmosphere, in addition to carbon dioxide, but there's also like sulfur dioxide and other pollutants. And so these things have a very similar effect. It's pretty much the same stuff as volcanoes put into the atmosphere, sulfur dioxide. And so our pollution has pretty much the same effect. When you put junk into the atmosphere, it blocks sunlight, and that actually has a cooling effect. However, we're pretty good at cleaning those up. So if you have a coal power plant, you could put a scrubber on it, and then that kind of collects the sulfur dioxide before it goes into the atmosphere. And so between about the end of World War II and the 1970s, at that time we had really fast economic growth, and so we were building a lot of coal power plants, and so we were putting a lot of junk into the atmosphere, a lot of the sulfur dioxide, and it started to cause acid rain. And so that had all kinds of problems. It was causing respiratory problems in people. With the sulfur, the acid rain was causing problems for vegetation. So people decided we need to do something about this, and we passed the Clean Air Act, or actually we updated the Clean Air Act in 1970 to address the sulfur dioxide and this acid rain. And so that's why we now have these scrubbers on coal power plants to kind of capture all this sulfur dioxide before it goes in the atmosphere. And so we're pretty good at cleaning that up. And so the problem is when you burn fossil fuels, you're putting, there's a couple of things you're putting in the atmosphere: sulfur dioxide that blocks sunlight and causes cooling, and carbon dioxide, which is a greenhouse gas and causes warming. So if we're putting both of those, when we burn fossil fuels, both of those are going into the atmosphere, but now all of a sudden we're capturing the sulfur dioxide, the cooling component. Now we're only mostly putting warming stuff into the atmosphere, and so that masking effect that the sulfur dioxide was having, it's not as much masking the warming from the carbon dioxide anymore. And so it's good that we're cleaning that up, because now it's not causing acid rain anymore, but on the other hand, it's not offsetting that warming effect from the carbon dioxide anymore. So now we have to do something about the carbon dioxide. But it's an important point that the other pollutants from burning fossil fuels, they were masking some of the warming that we were creating by putting carbon dioxide and other greenhouse gases into the atmosphere. So there's actually another myth related to this. Since these pollutants are so similar, there is a myth that, well, actually, in volcanic eruptions, they put carbon dioxide in the atmosphere too. And there's a myth that people say, well, there's so much carbon dioxide put in the atmosphere from volcanic emissions, it's way more than humans do, and so human carbon dioxide emissions don't matter. Well, I mean, that's a myth, and I don't know if we're going to cover this in the Myths Week, but I thought I'd cover it now. Scientists measure the amount of carbon dioxide that volcanic eruptions put in the atmosphere and that burning fossil fuels put into the atmosphere. And fossil fuels are about, year by year, 100 times more carbon dioxide into the atmosphere than volcanoes on average. So we're dwarfing the amount of carbon dioxide going to the atmosphere from volcanic eruptions. Okay, so then we also have ocean cycles. Pretty much the most important one for the climate is El Nino. And so this is a picture of an El Nino and a La Nina. So you can kind of see that along the equator, in the Pacific Ocean, sort of off of Central America coast, when you get hot surface temperatures on the ocean surface, that's an El Nino event. And when you get so the red is hot, and then the blue and purple are cold. And so when you get particularly cold temperatures off of the Central America and the equator in the Pacific Ocean, that's a La Nina event. So pretty much what's happening is that water is cycling. It's a cycle of water in the ocean, and when warm water is being pulled up to the surface, and it's creating that El Nino, and that also warms surface temperatures because the surface of the ocean is warm, and so the air above the ocean is also warm. Whereas with the La Nina, you're getting colder water pulled up to the surface, and so since the ocean surface is cool, then the air temperature above the ocean is also cool. And so this has various effects on the climate. So we can kind of see how those have changed over time. So the key word with these ocean cycles is cycles. They're cyclical. And so you'll have like a positive cycle and then a negative cycle and a positive cycle and a negative cycle. And so over time, they average out. El Nino isn't particularly regular. So you can see like in the 1950s to 1970s, there were more La Ninas than El Ninos. And then in the 1980s and 90s, there are more El Ninos than La Ninas. And then since 2000, we started to have more La Ninas. And so there are periods when you have more of one or the other. But over the long term, they average out. You get the same roughly number of El Ninos as La Ninas. And so over a short period of time, over a few decades, you might have a warming influence from more El Ninos than La Ninas. But over the long term, over the past 60 years, it's been a pretty much zero effect on surface temperatures, because we've had roughly the same amount of El Ninos and La Ninas. And so it's basically the ocean water over, if you average it all out, it averages out to about zero change. So people like to focus on El Ninos because pretty much when we have a really big El Nino, it's bringing a lot of heat up to the surface and warming the surface air temperatures. And when we talk about global warming, we're usually talking about surface air temperatures because that's where we live, that's what affects humans because we're on the surface. I'm feeling right now the surface air temperature. And so we get the hottest years when we have the biggest El Ninos because it's just bringing a little bit of extra heat up from the ocean to the air. And so pretty much when you have a record-breaking hot year in terms of global surface temperatures, it's usually because you have a really big El Nino. So 1998 for a long time was the hottest year on record because it was a monster El Nino. You can see it's a big spike in the late 1990s. And so for a long time, for about 15 years almost, it was actually about 10 years, it was the hottest year on record. And then this was a source of climate denials. People are saying it's not even as hot as 1998 yet, so global warming must have stopped. But then, eventually we had another El Nino year, and combined with global warming, it broke the record again, and all of a sudden, we started having a few more El Ninos, and then combined with global warming, we started to break a lot of temperature records. So it's just important to realize that these cycles do impact short-term temperatures, and they can impact a particular year significantly, but over the long term, the average effect is basically zero. So another key cycle is the Earth's orbital cycles, and they were kind of calculated by this guy Milankovitch, and so we call them Milankovitch cycles, and we'll probably talk about him more next week when we talk about climate science history. But so basically, there are various different cycles that the Earth's orbit goes through. For one thing, we don't have a perfectly circular orbit around the sun. It's kind of oval-shaped. And so at some times, the Earth is further away from the sun than at other times in its orbit. And so when it's closer to the sun, obviously it's going to be more energy from the sun reaching the Earth, and so it's going to be warmer because of that. The Earth also kind of tilts and wobbles throughout its orbit around the sun. And so actually, in the next slide, we're going to have a video of a climate scientist explaining this. But basically, that's an important factor determining how much ice there is on Earth, which therefore determines the reflectivity of the Earth and therefore determines how much energy is outgoing and incoming. So I'm just going to have the climate scientist explain that in this video. This is from a congressional hearing. This is Dana Rohrabacher, who's a representative from Southern California who is, let's be real, he's a climate science denier. And he's going to be talking to Richard Alley, who's this kind of brilliant climate scientist from Penn State, I believe.
Dr. Alley, with all due respect, you didn't answer the chairman's question. You know, the question was a very good question. There have been these back and forth between on glaciers and the melting that we've seen over and over again. Why did it happen then if these same factors that you're blaming it on didn't exist then?
I can give you as much or as little answer as that you would like.
Give me 15 seconds.
Okay, give me 30 if I may.
Okay,
the ice ages are caused by features of Earth's orbit. Your brightness is the sun. This is the Earth.
Right.
This is the equator. Here is the North Pole.
Yes.
If the North Pole stood straight up, you could
Right.
never give me a sunburn on my bald spot. But in fact, as you know, it is tipped over a little bit, and it nods a little more and a little less over 41,000 years. Now, when it nods more,
Right.
my bald spot ice melts and the
Right.
equator is a little more shaded, and now the ice grows and now the ice melts. But it takes 41,000 years for this change to happen. We know what that's doing right now, and it's not fast enough to explain what we're seeing.
Okay. Good explanation, right? I love that explanation. So, on your head, North Pole is the equator, or is the bald spot. I don't have a bald spot. But in any case, in the North Pole, or in the poles, there's a lot of ice, or at least there is when the planet's relatively cool. And so if the planet tips a little bit in its orbit, more of the North Pole is facing the sun, and so more ice will melt because it's getting sunlight hitting it. And so that's going to make the ice melt in the Arctic. And then so because ice is much more reflective than the oceans or the land below it, that's going to decrease, in particular in the Arctic, but overall for the planet, it's going to decrease the reflectivity. And if you're decreasing the reflectivity, that means suddenly the Earth is going to be absorbing more sunlight, and that's going to cause more warming, which in turn is going to cause more ice to melt, which is going to cause more warming. You get this feedback cycle where you get warming, ice melting, warming, ice melting. And so that, just because the Earth's orbit happened to tilt a little bit and melt that ice, that's going to cause this warming effect. And so that's why there are these cycles. As Dr. Alley mentioned, this particular cycle is a really slow one. It takes 41,000 years to happen. And so on this slide, you can kind of see that. So this is data measured from ice cores. And so usually they're drilled in Antarctica, because Antarctica is frozen all the time. It's always below freezing. And so all you do is all that happens is when snow falls, it just stays there and it just builds up and builds up and builds up because it's not melting. And so when we drilled ice cores into Antarctica, the further down we're drilling, the further back in time we're going into older and older ice. And in that ice, there's air bubbles trapped. And so scientists, they drill the cores and they look at the cores and they look into the air bubbles, and they see how much carbon dioxide is in the air bubbles, and that allows them to reconstruct how much carbon dioxide was in the atmosphere way back in time. And they can also do similar things to figure out the temperature way back in time. And so this is a chart from one of those ice cores in Antarctica. It's from the Vostok ice core. And again, the red is the temperature in Antarctica, but it's the temperature over the past 300,000 plus years, and then the blue is the carbon dioxide over the past 300,000 plus years from these ice cores. And so you can see there's this kind of slow long-term cycle where it goes up and it goes down and it goes up and it goes down, and that's due to these orbital cycles that operate over very long periods of time, but they cause warming and cooling. So you can see at the bottom, that's kind of an ice age, and at the top, that's a warm period. Right now, we're at one of these top ones. We're in one of these warm periods. We came out of the last ice age about 12,000 years ago, or glacial period is what we call it. And then, so actually it says today, but today we're actually way up here with the carbon dioxide. We're way off the chart because naturally the amount of carbon dioxide in the atmosphere usually varies between about 180 and 280 parts per million. And now we're at 410 parts per million. So we're way off the chart in the carbon dioxide. And you can see how closely related the carbon dioxide and the temperature are. That's because of the greenhouse effect, which we're going to talk about in a few slides later. but they are very closely related. So again, if you see the carbon dioxide shoot up that fast, you're going to expect to see the temperature follow it. So again, we're going to talk about the greenhouse effect in a little bit here. So I mentioned those ice age transitions, and those are really a key component of the Earth's climate, so we're going to talk about those. And so basically what happens is you get these orbital cycles, they start the planet warming. And so as Richard Alley talked about, one thing that starts these, if we're going from, let's say we're going from a cool period to a warm period. So in the cool period, there's a whole bunch of ice on Earth, and suddenly the orbit changes, and suddenly some of that ice starts to melt. And because the ice starts to melt, the Earth becomes less reflective and starts to absorb more sunlight, and it starts to get warmer, and this particularly, at first, happens in the Arctic, because that's where the orbit starts to point the Arctic toward the sun. So when that ice melts, it's introducing a bunch of fresh water from the Arctic into the ocean. And so the ocean's salty, so then they get a bunch of fresh water, and it starts to disrupt ocean cycles. And so this is important. There are a lot of ocean cycles that kind of transport heat all around the Earth. And so one of the big ones is it's the Gulf Stream. And so the Gulf Stream sort of starts, you can say it starts, part of the Gulf Stream is it's in the Gulf of Mexico. And then it goes up the Atlantic, and it's basically transporting warm water from the equator up to Europe, up to England. And so England is actually at a really high latitude. It's kind of, I think it's similar to where Alaska is. But Alaska's cold. England is actually relatively warm. That's because of this heat being transported in this ocean cycle, the Gulf Stream, from the Gulf up to England. And so suddenly, if you start to disrupt these ocean patterns, these ocean cycles, then you're disrupting the Earth's natural heat transport, and it's going to mess with basically the temperature all over the Earth. And then another factor is that the warmer the ocean is, the less carbon it absorbs from the atmosphere. And so basically you get a release of carbon into the atmosphere as the ocean warms. And so putting that carbon in the atmosphere, since carbon dioxide is a greenhouse gas, that increases the greenhouse effect, and that has another warming feedback where the warmer the oceans get, the more carbon they put in the atmosphere, and then it gets warmer, and that warms the oceans, and they put more carbon in the atmosphere, and you get this another cyclical effect where you get this warming feedback. And so there was a really interesting paper, I think this was in 2012, from some climate scientists at Oregon State, where they looked specifically at how the planet warmed during this transition from an ice age, the last ice age, 12,000 years ago is when it ended, to this warm period in the present. And so in this chart, you're looking at temperatures at different latitudes on Earth. So the purple one is the Arctic, and then the red one is the Antarctic, the north and the south. And so you can see about 20,000 years ago, basically we had one of those Milankovitch cycles happened, and the North Pole tilted toward the sun, and so the North Pole started to warm because ice was melting. And so that caused the ice to melt and the Arctic to warm, and then that put a bunch of fresh water into the ocean, started to make the ocean less salty, and started disrupting these ocean cycles. And so that caused sort of the southern part of the, basically disrupted the transport of heat, and it caused the Southern Ocean to start warming. And then so the Southern Ocean started to warm. You can see the orange and the red the temperature starts to go up. And then because the oceans start to warm, they start to absorb less carbon dioxide. So carbon dioxide starts to build up in the atmosphere, and so they have a nice line here showing the onset of the carbon dioxide rise when we start to get this cycle where the oceans warm, more carbon dioxide goes to the atmosphere, they warm some more carbon dioxide goes to the atmosphere, and carbon dioxide goes to the atmosphere, gets mixed throughout the entire atmosphere, and so it starts to warm the whole planet. And so then you can kind of see everything starts to warm at the same time. It takes a little while for the Arctic to start warming again, but because of that CO2, carbon dioxide going to the atmosphere, eventually the Arctic starts to warm again too, and so then basically the whole planet gets kicked into a warming phase. And we can put it all together they put it all together in other charts. So what we have here is the yellow dots are the carbon dioxide level in the atmosphere starting 20,000 years ago. The red is the temperature in the Arctic, which they got from the Arctic ice cores. And the blue is a reconstruction of the Earth's average temperature on the surface. And so basically you can see about the same time the temperature in the Antarctic starts to go up and the Southern Ocean starts to go up. And then that makes the carbon dioxide level go up. And then following that, the Earth's average temperature goes up as the North starts to warm again too. So there's this complicated interconnections between the North and the South. and all these ocean cycles and the heat and carbon dioxide. But basically the point is that the natural cycles start the warming happening, and then these feedbacks like carbon dioxide being released from the oceans kick it into high gear and make these transitions from ice ages to warm periods possible. And so we're seeing something similar now in the Arctic. It's not the same sequence of events, because the first thing that happened now is that now we're just immediately pumping carbon dioxide straight in the atmosphere. We're not waiting for the poles to warm and the ocean cycles to get disrupted. We're just putting carbon dioxide in the atmosphere. But that's having a similar effect on the Arctic. And so this is going to be a video. A colleague of mine, Andy Lee Robinson, created this. And so on the left, this is an ice cube, represents the volume of ice in the Arctic in 1979. And then as the video goes, this right ice cube is going to show the volume of ice every subsequent year. And there's also going to be this red line is going to show how the Arctic ice volume has changed in every given year. And he's also a pianist, so he put some nice piano music in the background. So over the past 40 years or so, we've lost about 3/4 of the ice volume in the Arctic. That's because a lot of the older ice that was thicker, that in particular is starting to melt because the ocean waters are warming. And so, as you would expect, this has implications for the climate system all over the world, because we just saw in this past slide, it's not just the Arctic doesn't act on its own. When the Arctic changes, then it causes changes in ocean patterns. It also causes changes in atmospheric patterns. And so because of these changes in the atmosphere, we're actually seeing changes in the jet stream, which is basically, the short story is that weather patterns are tending to get stuck in one place. They're tending to get blocked because the jet stream has kind of slowed down and become wobbly because of changes in the Arctic. And so that's causing, for example, right now it's causing changes in hurricane patterns. And so we're seeing right now hurricanes that kind of get stuck in one place. That's because, in large part, because of these changes in the jet stream, which are connected to changes in the Arctic. And so it's a really important point that, every part of the climate system, you can't look at it by itself. It's all connected to other parts of the climate system. It's all kind of one large interconnected web. And so I think this is probably a good place to take a break. We're going to go over the greenhouse effect next. And so that's an important point. So let's take a break here. Let's come back at about 11 o'clock. And then we'll go into the greenhouse effect.